Hello and welcome back to Unit 7. In this part of Unit 7, we're going to take the two concepts we've learned thus far in this unit and bring them together. So we're going to merge the idea of work and energy and get to the work-energy theorem. And for this, we're going to derive the work-energy theorem. So to do this derivation, we're going to consider a little chunk of work, which is going to be, not a W, let's see. Let's try again. The net force dotted with dr by definition. So a little chunk of the network will be the net force dotted with a little chunk of displacement. And now I'm just going to substitute in Newton's second law, that F net equals ma. And then I'm going to substitute in the definition of acceleration being dv dt. Now, this next step is one that when I first saw something like this done, I remember looking at my physics professor and just saying, you can't do that. You can't do that. And he looked at me and he said, but it's just divided. Why can't I do that? Which allowed me to go, well, I don't have a good answer to that, and stopped complaining. So what is this mystery next step? I'm going to take that dt and slide it over. It's just divided. And now I'm going to look at this new thing that I've made, this dr dt sitting right there, and I'm going to realize that by definition, that is the velocity. And because dot products are commutative, I can rearrange this to be nv dot dv. Okay. And that is this little chunk of work. Now, what I really want to know, though, is not a little chunk of work. I want to know the total work. And to find the total work, I've got to integrate. So I'm going to integrate my d net work from a to b, and that will be the integral from a to b of mv dot dv. Okay, now remember, v is vx I hat plus vy j hat plus vz k hat, and dv will be a dvx I hat plus a dvy j hat plus a dvz k hat. So when I take this dot product, pulling the m out in front, I have vx times dvx plus vy times dvy plus vz times dvz. Okay, well, I can do these integrals. Each one is the velocity multiplied by the differential element of that velocity. So each one will take the form of 1/2 times that velocity component squared. Okay, and that's all evaluated from A to B. Well, I'm going to pull that factor of 2 out in front. Okay, and now look at that piece that's in parentheses, vx squared plus vy squared plus vz squared. Well, that by definition is v squared. And now we have 1/2 mv squared evaluated at B and at A, but 1/2 mv squared is the kinetic energy. So this will equal the kinetic energy at B minus the kinetic energy at A, or in other words, my total work that I get from integrating this little differential element of work is going to equal the change in kinetic energy. And that is the work energy theorem. And now let's apply it. First, we're going to consider a 2 kilogram block moving at 4 meters per second coming to rest after traveling 1 meter in a straight line. Okay. Now, there are lots of ways we could go about figuring this out, but it says specifically for us to use work and energy considerations to figure out what is the work done by friction. Okay. Well, let's call this part A, if you will, and this part B. Let's start thinking about part A. We know work equals the change in kinetic energy, which will be 1/2 m v final squared minus 1/2 m v initial squared. But that also equals a force times a distance times a cosine of an angle. And let's not call that a distance. Let's instead call that a delta R, a displacement. Okay, well, the force in this case is the force of friction. And if we think about the forces acting on our object, we're going to have some sort of normal force between the surface and the object. We will have the object's weight, and we will have friction acting in the opposite direction from the displacement. So this force will be friction. We're given delta R. We're told it travels 1 meter, so we know that. The angle, let's actually plug in numbers, shall we? We know it travels 1 meter. The angle is 180 degrees because the force of friction and the displacement point in opposite directions. The mass we're told was 2 kilograms. Final speed is 0 because it comes to rest. And initial speed was 4 meters per second. And if you put this all into a calculator, you find that the force of friction is equal to -16. And I am jumping ahead. Pardon me. Because we didn't want to know the force of friction, we wanted to know the work. So we didn't need to do any of this yet. So we find the work due to friction as -16 joules. Okay, for part B. Part B is where we need that piece that I just erased. So we know the work that friction does is -16 joules. And as we just investigated, the force of friction on the object times delta R times a cosine of 180 degrees has to equal -16 joules. And that displacement we know is 1 meter. This tells us that the force of friction is 16 joules. No, flip that. Wrong unit. It's a force now, so it's 16 newtons. Okay, so remember 1 joule is 1 kilogram meter squared per second squared, but it also equals 1 Newton meter. And that is, the latter definition is the one I used to get my units here. And now I'm going to pull in the fact that the force of friction will be the coefficient of kinetic friction times the normal force. If I go back and look at the free body diagram I did, I have no acceleration vertically, so my normal force will equal the gravitational force. This is 16 newtons. The mass was 2 kilograms, and G is 9.8 meters per second squared. And if you solve for the coefficient of kinetic friction, you get 0.82. For the next example, we have a car that is increasing in speed. And we are told that the speed increases by a total of 50%. And we want to know, assuming nothing else changes other than the fact that the car is moving faster, how long will the minimum braking distance change? Or by how much will it change? Okay, so we're going to make an assumption here. And the assumption is that the initial speed that it was going, I'm going to call v, and the new speed, the one that is 50% faster, will be 1.5 times v. Okay. And now I'm going to think about what is going on in this problem. Here I have my car moving at my speed v, or it could be 1.5 v, but it's what it's doing initially. And over here, some distance away, it's no longer moving. I'm going to call this spot or this distance as what I want to find. What is the displacement? What is the minimum braking distance to make this happen? I know that the work has to equal the change in kinetic energy. So that would be the force times that displacement times the cosine of an angle has to equal 1/2 mv initial squared, v final squared minus 1/2 mv initial squared. Okay. If we think about the forces on the car, you will have a normal force pointing upward, gravitational force pointing downward, and you will have a frictional force pointing opposite the direction of motion. Since I have this car moving to the right, I'm going to let the friction point to the left, which means this angle will be 180. So the friction between the surface and the car times delta r times the cosine of 180 degrees. V final is 0. That leaves me with 1/2 mv initial squared. And now I can solve for delta r. Delta r will equal mv initial squared over 2 times the frictional force. Now it tells you in the problem, assume everything else is the same. The only difference is the velocities. So this is all the same. Okay. So now somehow I exited my PowerPoint. Dreadfully sorry. Okay, back at it. I found just now that delta r equaled m over 2 times the force of friction times v squared, whatever that initial velocity squared was. Well, the original one I had, I'm going to write as this. And then when I do the new one, I'm going to put this in as v nu squared. So this would be the original. And this one would be the new. I'm going to take and plug in that v nu is 1.5 times my original. And I'm going to square that. Not right now. Okay, 1.5 squared is 2.25. So I get 2.25 multiplied by m over 2 times the friction times v squared. So my new delta r is 2.25. Let me add some subscripts here. Times my original delta r. So even though the velocity went from 1 to 1.5, the stopping distance went from 1 to 2.25. So more than doubled. And this does complete this part of this unit.